All right, I have good news. I have an experiment that Gary could do. I'm going to start off with that. Then I'm going to explain why I don't want to have a fucktard kind of arguing about this kind of stuff. That's pointless from my point of view. All right, so uh, Gary was saying, "Oh, there'd be no way to tell what speed you were going," but then he'd realized right then, wait a second, you could tell by the deflection of the laser. That's right. So I went and did some math, and I also remembered something that I was overlooking, which is an interesting oversight, actually. Gary seems to have made it in his recent video where he talks about a microwave experiment that might work. And I've done some back of the envelope calculations, so it also relates to the Lego. But before I go into that, I did the math. Now, here's the beautiful thing. I had mentioned one of my videos, hey, we're moving 1,000 miles an hour or whatever. Yeah, that's around the surface of the Earth as it spins. That's not very much a fraction of the speed of light. But we're also shooting through space, going around the sun. That is a significant speed. That's 67,000 miles per hour. And that's about and you guys should check my calculations, but that's about 1/10,000th of the speed of light, which is a very handleable number because that means that a laser shooting just a mile is going to be off by a half a foot. And you don't need it off that far, so you don't need a mile-long laser. So if you do the math down, you'll see, let's say you want a 1/4 inch of deflection. Um, then 300 feet, 400 feet should do it. And here's the beautiful thing. There is no rectification in making sure you have right angles because there's this issue, and I was thinking about it too, and Gary brought it up. It's like, well, how do you align things if you can't trust the lasers are going straight? Because, yeah, we use lasers to go straight. If you point a laser north and you have a target way north, you expect it to have gone due north, not that it would skew. Okay. So here's the beauty of this is that we are on the surface of the Earth, right? So as the Earth shoots through space, we're spinning on it. So that means when we're on this side of the Earth, we're going with it, 67,000 miles, and it's eastward. But then we go around to the other side of the Earth. Well, we're still going 67,000 miles an hour this way, but we're on the other side of the Earth. So now it would be westward, right? And at noon and midnight, is that right? Yeah, at noon and midnight, no. Well, forget which times of day. I didn't prepare to think which times of day we're talking about. Noon and midnight are the high speed, and then 6 and 6 are when we'd either be shooting mostly upward at that speed or downward. So if you just leave your laser on all day, point it at a piece of graph paper, and mark the graph paper every couple of hours, it should do a little ellipse, right? It should do a little ellipse. Won't be a perfect circle because we're on the angle of the Earth. And even if you go to the equator, it'd probably look mostly like a circle, but it wouldn't be quite a circle because the tilt of the Earth. And if you were at a North Pole, it'd be mostly a line back and forth, a collapsed ellipse. So you could do this with an almost regular laser. Now, I've shot a laser a mile before from my aunt's deck and gone over to where it was hitting to see how big it was. And, it was like a meter at that distance. So that'd be hard to figure out the center of it. So you might need a decent laser that at least doesn't disperse much over, a few hundred feet, a tenth of a mile. Now, if Gary's right, when you go out every couple hours and mark where the dot is, it'll make this shape. Now, of course, that's not going to happen. I know for various reasons. One, the Michelson-Morley experiment is based on the same principle, but it uses interference, which is a very sensitive way to notice a phase shift in a wave, right? So you could definitely do this experiment instead. But here's the thing with LIGO, you've got lasers going at right angles. And they go like 4 miles, but then they bounce back and forth so many times that they also, double and triple and quadruple. And I think that it's going 1,000 miles in the end or something like that. Now, Gary's idea is that these lying scientists, what they do is, they're trying to get the spot on. And so it's like, oh, the spot's off to the left. Knob. Oh, it's back on. The problem is, at that distance, the laser point would wander by feet, by many, many feet, yards, throughout the day. So every minute, you'd have to change it. I think they'd notice that. It would be such a huge conspiracy if they had to do that. And they're like, we don't know why we do this, but, just ignore it, everybody. This is behind the curtain stuff here. So LIGO wouldn't even work if this was true. So it's going to be a null result. You'll find that laser throughout the day keeps in the same spot, and it only moves if you bump the laser or move the target. So make sure everything's fixed in place really well. So I'm very confident that's not going to happen, a positive result with that experiment. But it's a fair experiment, and I would definitely be happy to see Gary do it. I was happy when Gary realized that you would be able to tell what speed you were going. It'd be very easy with a laser to tell what speed you were going, because we have detectors that can tell if the laser just moves a little tiny bit, so it wouldn't even have to shoot a mile or anything like that, as long as you had a detection device that was able to measure the shift down to the millimeter, which would not be difficult technologically, though not cheap probably either. Though we're just talking about thousands of dollars, I think, at this point. But so yeah, now the other thing is why I don't want to have the fucktard type conversation about this stuff. I'm not one of these people that's saying, hey, in order to understand the universe, we have to know all the little fundamental bits down at the reductive bottom, then we could build it back up. I'm a skeptic. I believe that down at the bottom where the axioms and fundamental truths live, there's always actually more questions. There's more to know about those things. Right? Because my epistemic center is I don't believe we can start from the bottom. That can never happen. We don't start from the top, the big picture. No, we start in the middle where human beings are. And what I know of the universe is that I have a series of impressions, visual impressions, sound, also emotions, even memories come to me as fresh impressions. They feel like they're from the past, like it's something I've seen before. And even if that's true, and I believe that, there's some truth to that those memories were created in the past and I'm recollecting them, the fact is then I have an impression. Even if I decide to go up and get myself a cup of coffee, I actually just have impressions of me wanting to do that, impressions of me going, I'm going to do it, and impressions of being inside the camera of my body, going upstairs and getting it. All I have is a series of impressions that includes all the sense data, all the emotions, feelings like hunger, lust, all of those come for a limited period of time in a series, right? And I'm working my way out from the middle. So I don't yell at people about disagreeing about whether, atomism, is it true or not? I like discussing it. I love abstractions. I like working my way far out from the middle to the various big picture and small picture extremes. But my epistemology, the way I believe knowledge works itself, is not conducive to calling someone a liar because, for example, they don't believe in relative velocity. I believe they're wrong because I've gotten enough information, right? Much of it's secondary, granted, but I don't just trust secondary information. I've also had primary information. I took college physics, and for like 2.5 years, still had to focus on my degree. Going up to the point of, the Michelson-Morley experiment was, I think, the most sophisticated or significant experiment I did. But there's a lot of other experiments as well. And then you have a reference frame, and, so trusting certain results, the data from certain results, that it wasn't lied. It might be a mistake, and the person might be lying to themselves, and that lie might be a part of the mistake. That's like me believing that Peru exists, even though I've never been there. There's so much corroborating evidence that even though I've never been there, I could go ahead and make a judgment. I've never been to Australia, and I think the president of Australia that Trump just argued with is a real person, and that's a real position in a real country. Okay, so I've gathered this extra information, and I'm pretty sure that if Gary does this, I mean, I'm totally sure, but who knows? If Gary does this experiment, the laser spot will stay put, assuming, the laser and target are both fixed, right? Because of all this other secondary data. And plus, I have done the Michelson-Morley experiment, which proves through a different way that there is no relative motion between light and anything else except for yourself. It always goes at light speed relative to yourself. And Gary could say, oh, it would never happen. And that's like Aristotle. Aristotle was smart, but he didn't believe in experiments. He just said, hey, heavier things fall faster. Why? Because obvious. And at the time, that was a contribution because people weren't even thinking about that stuff, let alone what was obvious or not. And then he gave us results that got shot down one after the other for centuries, and here we are. So yeah, I really think Gary, you should do this experiment, and there's a chance you could do it if you were careful how you measured the spot. Right? It's going to be hard if the spot is 2 feet across to measure, to mark where it is, its center. So that's a problem. So you might need to get a good laser, or draw the circle around the edge, something to keep you honest. But very doable because we are traveling at 67,000 miles per hour through space. And 6 months later, it's through space in the opposite direction. And you could definitely find out your absolute scalar velocity, if such a thing existed, with the help of lasers, if your theory works. Your theory doesn't work, so you won't be able to tell. And Galileo's statement 400 years ago that you'd never be able to tell, that's going to turn out true, because that is what sparked Einstein's contemplation of, if that is possibly true, then this other stuff must be true. Then we checked, and it was. And I think it's funny how when you watch my video explaining that the way that photon could work is because the time would go slow, you acted like you figured that out, and then you were watching my video. I find that difficult to believe, since so many times you had said, oh, how could that even possibly be? How could that? So you know how we're saying it could be, and you knew all along. And so you did a big exposition of what I was going to say while my video was paused, and then started and go, well, he better say that. And your idea is that we're asleep half of the time, I guess because the decay rate in the neurons or something. Well, let me just say, you're not asleep half the time. Time is compressed. You're getting the same amount of time, but it's compressed relative to someone else. Someone else has a bigger range of time in which they're watching your local time occur. So yeah, do that. Laser experiment. And, it's not even like, you're in the woods, so you could find some tree 500 yards away and just make sure you get a laser that keeps its point good enough. Put it over there, bang, 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 up some plywood, put the graph paper on there. Make sure you go out there every couple hours for a few days and mark it. According to your theory, you should mark an oval that repeats every day, right? But if you don't want to go 500 feet away, you could have 2 mirrors 50 feet away and just make sure the laser bounces 10 times, since the predicted deflection is all in the same direction. That will work as well. And you don't have to, the mirrors don't even have to be flat or nothing. All you have to do is have it go at least a couple hundred feet, a few hundred feet, and then it comes spitting out. The mirrors could be crooked as long as it comes spitting out and hits the target. You should be able to see it do its little oval. So I predict someone is very soon going to not get the Nobel Prize.